In previous lectures, we used derivatives to find the extreme values of a function. We checked whether a given function is increasing or decreasing on a particular interval, or we found the local maxima and minima by the help of derivatives. Uh, Now a question comes that which functions have zero derivatives? Obviously, we all know that constant functions have zero derivative, but could there be more complicated functions whose derivative is always zero? Or if two functions have identical derivatives over an interval, how are they related? Well, all of these questions will be answered by applying the mean value theorem and by applying the Rolle's theorem, which is a special form of the mean value theorem. Now let's discuss the mean value theorem. Now the mean value theorem says that the hypothesis of a mean value theorem is the given function should be continuous on a closed interval and should be differentiable on an open interval. So if a function satisfies this condition, then there must be some point C in that open interval at which the instantaneous rate of change is equals to the average rate of change. Now here it's we can see clearly that this is a function and it is continuous and it is differentiable on an open interval a and b. Then in that particular interval a and b, there will be some interior point C at which the instantaneous rate of change is equals to the average rate of change. Now the physical interpretation of a mean value theorem says that at some point, at some interior point, the instantaneous rate of change must be equals to the average rate of change over the entire interval. And the example is that if you drive between the 2 points A and B, then at some time your speedometer reading was the same as your average speed over the drive. Now this is the detailed example of the mean value theorem. You can study that. Now in this example, we can see that we are taking a function x square which is continuous on a closed interval 0 to 2, and it is differentiable on an open interval 0 to 2. At the end points, the function have the value 0 and 4. So the mean value theorem says that at some point C in the interval, the derivative must be equals to the average rate of change. So when we are putting the derivative equals to the average rate of change, we are getting a value of C that it is equals to 1. So that means that in the interval 0 to 2, at point 1, the average rate of change is equals to the instantaneous rate of change. Well, it is not always easy to find out C, but in most of the cases we can find out C by using some algebraic manipulation. Okay. Now let's discuss the specialized case of the mean value theorem, that is the Rolle's theorem. It says that if a differentiable function crosses a horizontal line at two different points, then there is at least one point between them where the tangent to the graph is horizontal and the derivative is 0. Now we can see these two functions. Suppose that both of the functions are continuous on a closed interval and they are differentiable on the open interval. If f of a equals to f of b, then there exists a point C in that open interval a b at which the derivative at that particular point is 0. Now the differentiable curve has at least one or may have more horizontal points between any two. It may have more horizontal tangent between any 2 points where it crosses a horizontal line. Now in this graph we can see that there are 3 points at which the derivative of the function at the particular point at the interior points are 0. So the Rolle's theorem may be combined with the intermediate value theorem to show that there is only one real solution of an equation, f of x equals to 0 form. Now comes another example that if you bike up a hill, then back down at some point your elevation was stationary. At that particular point you just stop for a moment. Now here are some corollaries. In this corollary it is written clearly that a function whose derivative at each point of an open interval is 0, then that particular function is just a constant function. In corollary 2, it says that the geometric point of view of corollary 2 says that the graph of a function with identical derivatives on an interval can differ only by vertical shifts there. For example, the graph of a function with derivative 2x are the parabolas y is equals to x square plus c, shown here for selected values of c. Now see that all of these functions have the same derivative 2x, because these are the graphs of parabolas which just differ in their vertical shift. Like this is here c is 2, here c is 1, so this is the graph of function x square plus 2, this is graph of x square plus 1, this is a graph of x square, this is x square minus 1. So all of the given functions have the same derivative 2x. Now let's move towards the next example, that find the function f of x whose derivative is sine x and whose graph passes through the point 0 to 2. Now 0 to 2 is the condition, because there are a lot of functions there will be a lot of functions whose derivative will be sine x, but we are interested in only that function which passes through the point 0 to 2. Now the derivative of g of x is minus cos x. Since the derivative of g of x is minus cos x, so g dash of x is sine x. So f and g both have same derivatives. According to the corollary to f of x is g of x plus c for some constant. Since the graph of f passes through the point 0 to 2, the value of c is determined by the condition f of 0 equals to 2. So substitute the value in the equation, we get c equals to 1. So f of x equals to minus cos x plus 3. This is the function whose derivative is sine x, and this function passes through the point 0 to 2.
Now let's discuss exercise 4.2. In question number 4, we have to find the value of c that satisfies the equation the average rate of change equals to the instantaneous rate of change in the conclusion of the mean value theorem for the function and intervals. Now here is the question. F of x is under the radical x minus 1 and the interval is 1 to 3. So the average rate of change f of 3 minus f of 1 divided by b minus a, that is 3 minus 1, equals to the instantaneous rate of change. Okay, calculating the values, we get a value of c equals to 3 by 2. In question number 5, the function is changed. It's a trigonometric function, inverse trigonometric function over the interval minus 1 to 1. So the instantaneous rate of change equals to the average rate of change. Doing algebraic manipulation, we get the value of c approximately equals to plus minus 0.771. Now in the next question 10, we have to satisfy the hypothesis of the mean value theorem on the given interval, and if the function does not satisfy the hypothesis of the mean value theorem, we have to give the reason for the answer. Now in question number 10, the function is x raised to the power 4 by 5 over the interval 0 to 1. Now what is the hypothesis of the mean value theorem? The hypothesis of the mean value theorem is that the function should be continuous and differentiable. So this given function is continuous for every point on the interval 0 to 1, and it is differentiable for every point 0 to 1. So this satisfies the hypothesis of the mean value theorem. Now in question number 16, we have to find for what values of a, m and b does the function, this piecewise function, satisfy the hypothesis of the mean value theorem on the interval 0 to 2. Now function must be continuous at point x equals to 0 and x equals to 1. These are the break points. So at point 0 we have to check the right hand continuity. For that, the right hand limit should be equals to the functional value, so we get a value of a equals to 3. Now checking the left and right hand limit at point 1, I am getting this value. The function should also be differentiable at x equals to 1. So for that I am finding out the left hand derivative and right hand derivative at point 1. So I'm getting the value of m equals to 1. Substituting this value of m in the equation 1, I get b equals to 4. So the value of the unknowns are a equal to 3, m equals to 1, and b equals to 4. Now in moving towards question number 21, we have to show that the function have exactly 1 0 in the given interval. In question number 21, I can see this function. Now here we are using the intermediate value theorem. Intermediate value theorem states that if if we have selected an interval on and on the left side, on the left end point of the interval, if the function is giving negative value, and on the right end point the function is giving the positive value, then it means that it is then the intermediate value theorem says that if there is a guarantee that between those endpoints a root lies. So here we are just checking that do this function have a root in this interval. So by substituting these values in the function, we are getting different values, alternate signs of the function, so which says that or which guarantees that according to the intermediate theorem that there exists at least 1 0, which is basically the root. Now in question number 43, we have to find out the velocity and initial position of an object moving along a coordinate line. We have to find the object's position at the time t. Okay, now here velocity is given and a condition is given. We have to find out that what is the actual position function whose velocity is this. So 9.8 t plus 5, the function whose derivative is this is 4.9 t square plus 5t plus c. Now what is the value of c? By substituting this condition, we can find out the value of c, that is 10. So the actual function whose velocity was this is 4.9 t square plus 5t plus 10. Okay, now in question number 51, we have to check the temperature change. It took 14 seconds for a mercury temperature to rise from minus 19 degrees centigrade to 100 degrees centigrade when it was taken from a freezer and placed in the boiling water. Show that somewhere along the way the mercury was rising at a rate of 8.5 degrees centigrade per second. Now we know that this can be found out by using the mean value theorem. So the temperature T of t is the temperature of thermometer at time t. At t equals to 0, the temperature is minus 19 degrees centigrade, and at t equals to 14, its temperature is minus 100 degrees centigrade. So from the mean value theorem, there exists an interval such that the average rate of change equals to the instantaneous rate of change. So the rate at which the temperature was changing at time t equals to t naught as measured by rising mercury on the thermometer. Now here is
Now, after discussing all the concepts, here is a worksheet in which few questions are given, and by solving these questions, you can check your understanding of the concept.